Hey everyone, and welcome to this high-yield explainer. Look, if you're gearing up for your JEE or NEET exams and you just want to cut through all the noise, you're in exactly the right place. Today, we're setting the stage for you to absolutely master electrochemistry. Because honestly, this isn't just about rotely memorizing some equations. It's really about understanding the fundamental flow of energy so you can confidently tackle literally any problem the examiners decide to throw your way. So here's our quick roadmap for today. We'll start with powering the modern world, then move into the story of electron flow, mastering standard electrode potentials, the Nernst equation and Gibbs energy, solving target exam questions, and wrap it all up with a final exam revision checklist. Let's get to it. Okay, part 1. Powering the modern world. Before we get completely bogged down in heavy math, we've got to realize that electrochemistry is so much more than dry textbook theory. What we're really studying here is the fundamental link between chemical and electrical energy. It's a huge, interdisciplinary subject with massive real-world applications. Like, this is how we manufacture essential stuff like sodium hydroxide and chlorine. It's the science behind the batteries and fuel cells running our modern tech. Actually, it's even the reason you're understanding my words right now. Because the transmission of sensory signals to your brain? Yep, electrochemical. And looking forward, it's literally the foundation for building highly efficient, eco-friendly technologies.
Moving right along to Section 2, the story of electron flow. Now that we know what's at stake, let's zoom into the micro level and meet the real star of the show, the electron. To truly grasp galvanic cells, like the classic Daniel cell, you just need to follow the electron's journey. Treat it like a story, and it'll be a breeze to recall during your exam. Step 1. Over at the negatively charged anode, zinc oxidizes and dissolves right into the solution, kicking out electrons. Step 2. Those freed electrons travel through the external wire. And remember, they always flow from negative to positive. Step 3. They hit the positive cathode, where they reduce copper ions, depositing solid copper. Oxidation at the anode, reduction at the cathode. Simple as that.
But hold on, if electrons are only moving in one direction, wouldn't the charge just build up and totally kill the reaction? Well, yeah, and that brilliantly highlights why we absolutely need our next concept, the salt bridge. Think of a salt bridge as a connection between the two electrolytes. It lets ions flow back and forth to keep the internal charge perfectly balanced, all without letting the two actual solutions physically mix together. Without it, the whole system just comes to a grinding halt. So a massive foundational pitfall for a lot of students is mixing up the two main types of electrochemical cells. You cannot afford to get these confused on exam day. A galvanic cell, which we just walked through, takes a spontaneous chemical reaction and extracts electrical energy from it. It does the work for us. An electrolytic cell is the exact opposite. It takes external electrical energy from a plug or battery and uses it to force a non-spontaneous chemical transformation to happen. The quick way to remember: galvanic is spontaneous chemistry making electricity. Electrolytic is electricity forcing chemistry. All right, Section 3, mastering standard electrode potentials. So, how do we actually measure the potential or the pull of these individual half cells? The tricky part is you can't measure a half cell in isolation. So scientists just agreed on a baseline. That baseline is 0.00 volts. It's a completely arbitrary value assigned at all temperatures to our universal reference point, the standard hydrogen electrode. You are practically guaranteed to be tested on how to construct a standard hydrogen electrode, or SHE. So here's your 4-step, highly actionable checklist to lock this down. First, you use solid platinum as an inert electrode. Why platinum? Because it doesn't actually react itself. It just provides the physical surface for the oxidation or reduction to happen. Second, you bubble hydrogen gas over it at exactly 1 bar of pressure. Third, submerge the whole thing in an acidic solution where the concentration of hydrogen ions is exactly 1 molar. That specific setup, by definition, is 0 volts. Once we compare every other element to that hydrogen baseline, we get our complete table of standard electropotentials. Now, here's a serious memory shortcut. Do not try to memorize the entire table. Just know the extremes. Right at the very top, fluorine gas has the maximum positive potential. It desperately wants to grab electrons and get reduced, which makes it the absolute strongest oxidizing agent. All the way at the bottom, solid lithium has the lowest, most negative potential. It wants to oxidize and give electrons away, making it the strongest reducing agent in aqueous solutions.
Moving into Section 4, Nernst equation and Gibbs energy.
Okay, let's enter the math matrix. Those standard potentials we just discussed, they only apply when concentrations are exactly 1 molar.
But in the real world, and definitely in your harder exam questions, they rarely are. Enter the Nernst equation. This absolute beauty of an equation lets us calculate the actual cell potential, E cell, at literally any concentration. It takes the standard potential, E naught cell, and adjusts it based on temperature, the number of electrons transferred, and the reaction quotient, Q, which is just the ratio of product concentrations to reactant concentrations.
Listen up, because this is where so many students lose easy points. First, when you're calculating your E naught cell, remember the convention. It's the standard potential of the right-hand cathode minus the left-hand anode. E right minus E left. Second, and I can't stress this enough, always balance your redox equation first to find N. If you get the number of transferred electrons wrong, your entire Nernst calculation falls apart. Trust me, double-check N. Now let's connect this to thermodynamics. Examiners absolutely love testing the relationship between Gibbs energy and standard cell potential. Standard Gibbs energy equals negative N times Faraday's constant times the standard cell potential. If you're trying to figure out the maximum reversible work you can get from a galvanic cell, this equation is your best friend. It proves that the electrical work done is exactly equal to the decrease in the system's Gibbs energy. Let's ground this with a classic textbook example so it really clicks. For a standard Daniell cell, we know zinc and copper transfer 2 electrons, right? So N equals 2. Faraday's constant, F, is roughly 96,487 coulombs per mole, and the standard cell potential, E naught, is 1.1 volts. Plug all that in. Negative 2 times 96,487 times 1.1, and that gives us negative 212,271 joules per mole, which perfectly translates to a maximum reversible work of negative 212.27 kilojoules per mole. Easy points.
Awesome. Section 5. Solving target exam questions.
You're doing great. Let's put all this theory to the test right now. Here's in-text question 2.2 straight from the source. Can you safely store a copper sulfate solution in a zinc pot? Think about it for a second. This is directly testing your active recall of standard potentials and predicting if a reaction will spontaneously happen. The answer is a massive, resounding no. And here is the exact logic you need to write down for full marks. Zinc sits lower on the standard electrode potential table than copper. Because it has a lower reduction potential, it acts as a much stronger reducing agent. So if you pour a copper solution into a zinc pot, congratulations, you've just spontaneously created an electrochemical cell. The zinc pot is going to act as an anode, it'll undergo oxidation, and it will quite literally dissolve into the solution to replace the copper. Your pot will vanish, and you'll have a huge mess.
And honestly, that dissolving pot example brilliantly shows why understanding spontaneous reactions is so crucial for modern engineering. Just look at a rechargeable nickel-cadmium cell arranged in a compact jelly roll design. By meticulously picking materials with specific standard potentials and carefully separating them with a moist layer, engineers harness those exact same electrochemical reactions to power our everyday devices, over and over again, completely safely. But hey, even the best standard batteries eventually die or need to be plugged in. Which brings us to fuel cells. These are designed to take the energy of combustion from fuels like hydrogen or methane and convert it directly into electrical energy. Unlike a regular battery, a fuel cell has a continuous feed of reactants and a continuous removal of products. Because it totally skips the messy thermal combustion steps of a traditional power plant, a hydrogen-oxygen fuel cell runs at an incredibly impressive efficiency of about 70%. And the best part? Its only byproduct is pure water.
Almost there. Section 6. Final exam revision checklist.
Let's sprint to the finish line with a rapid-fire review. I highly recommend taking a mental screenshot of these facts because these high-yield definitions are almost guaranteed to show up. First, Kohlrausch's law of independent migration of ions. You gotta know that molar conductivity at infinite dilution is simply the sum of the individual ion contributions, period. Second, remember that while overall conductivity drops when you dilute a solution, molar conductivity actually increases with a decrease in concentration. Counterintuitive, but true. And finally, never forget that rusting and corrosion are fundamentally electrochemical phenomena. They're basically just unwanted natural galvanic cells happening right on the surface of metals.
All right, you've mastered the electron flow, you've conquered the Nernst equation, and you've nailed the thermodynamics. But I want to leave you with one final provocative thought drawn straight from the text. If electrochemistry is the ultimate key to generating continuous 70% efficient, hyper-eco-friendly electricity from something as simple as hydrogen and oxygen,
Is the so-called hydrogen economy our inevitable future? As you dive back into your exam prep, just remember, the standard potentials and equations you're grinding through today are the exact same principles scientists are using to power tomorrow. Keep studying hard, and I'll catch you in the next explainer.